All right, everybody, we're back for part 2 of today's lecture. Hopefully the exam review was helpful for you. Now we're just going to go over a brief little introduction to heart rate regulation and cardiovascular physiology. So intrinsic regulation of heart rate and the Frank-Starling mechanism. So let's start off with our intrinsic regulation of heart rate. Kind of if we think of the word intrinsic overall, we know that means within ourselves. We think of a person who is intrinsically motivated, that is a person who you don't have to necessarily call to wake up in the morning to go work out. This is a person who, regardless of if you get in touch with them or not, they're going to go work out. And that's kind of the same way the heart works. There's intrinsic regulation where that heart is going to beat without you having to think about it beating, or without some other input coming from another place in the body. So if we think about this, this comes through kind of the pumping of the heart happens through 4 different areas. The first area is our SA node, sinoatrial node, and that's kind of right behind the right atrium. Okay, so if we had to kind of draw this on here, we can get our white pen going right here. We're going to kind of put it right over here, and here is our SA node. What's going to happen when that SA node spontaneously depolarizes, okay? So if we think about this in conjunction with or in comparison to our skeletal muscle contractions, when that action potential reached there and was propagating the action potential, that was due to an influx of calcium or an influx of a neurotransmitter that's going to cause that depolarization due to a change in voltage overall because of that neurotransmitter being sent there. However, with the heart rate, there is none of this. This is a spontaneous depolarization. So when that happens, we're going to send our action potential to our second part, our AV node, arterial ventricle node, okay? And that one is right between the artery, or between the atrium and the ventricle, kind of right in the middle right there, okay? So that action potential is going to move from the SA to the AV node. And if we think about how the heart beats and what the purpose of each of these different chambers are, this makes sense. The SA node is going to contract. When that spontaneous depolarization happens, that is going to happen in the right atrium first, and then because the left atrium is pretty darn close, it'll happen there just a split second afterwards. As that is happening, an action potential is being sent to the AV node, which is right by the ventricles. But if we think about where the blood needs to go, we need to think about the different parts of how this action potential is transmitted. Because if the action potential just came to this area right here and contraction occurred, okay, so this part, this kind of the septum between the different chambers is going to contract first. And that would mean that we'd contract kind of, and especially from this point, in this direction right here. But if we look at where the blood needs to go, which is out through the pulmonary and aorta right there, okay, that doesn't make sense. So let's go back in time here and talk about what happens next. Well, that AV node then transmits that action potential down the septum to our AV bundle. That's kind of right in here. And this is just a bundle of neurons right here that are going to help transmit this action potential. From there, oops, we'll go back to our white. You then have up and around the points of your heart your Purkinje fibers. And it's very important to talk about where these Purkinje fibers are down here at the bottom, okay? Because those drastically influence the way in which the heart contracts. So now what we're doing is we're moving that action potential down to the point of the heart down here. And now when that action potential reaches and the contraction starts, well, now we get this nice kind of toothpaste squeezing action. So if you think of your tube of toothpaste, that action potential is going to start at the point and move its way in this direction. And just like squeezing out a tube of toothpaste, you're going to now be able to squeeze out the ventricles to enable you to eject blood out through the right and left ventricles. Okay, so the intrinsic regulation of heart rate starts with the movement of action potentials through these 4 different points. Now, if we want to talk about how heart rate increases or decreases, we need to kind of draw a figure to start that out. So, let's draw this guy right here. And on our y-axis, we're going to have percent activation. This will be 0, and this will be 100%. And when we're talking about heart rate regulation overall, we're going to be referring to our parasympathetic, nervous system and our sympathetic nervous system. The last part of drawing this figure is we have to label our x-axis, and that's going to be our heart rate. And let's zoom in a little bit on this. There we go, right there. And up here, high heart rate, maximal heart rate, let's put 200 beats, okay? And then minimal heart rate, we'll put all the way down, we'll put here at about 30, all right? So that's our range of heart rates. And now, what's going to control where we are on that is going to be the balance of parasympathetic on one side and sympathetic on the other. So how those two balance is going to determine where our heart rate is. Which one is active? And if we think about sympathetic, we know that sympathetic is going to be out towards our 200. So let's draw our sympathetic. And if we want to draw this, we'll just draw kind of a little triangle that looks just like this. And what that'll look like is something like this. And then if we do the other side, we'll do our parasympathetic, which is our rest and digest. And that's going to look something like this. Now, if we removed both of these, you take any sort of neural stimulation to the heart away and let that heart beat, okay? What is going to happen is you're going to find the intrinsic heart rate, and that actually happens to be right about here, between about 100 and 110. But I know what most people are probably thinking right now. Well, if I'm just sitting here resting, I know that my heart rate is not at 100 to 110. My normal resting heart rate is going to be somewhere around 80, or maybe a little bit lower if you're well trained. I had a friend back in college who was on the rowing team with me, and he went into the doctor, and the doctor actually had him go in for a test because his resting heart rate was about 34 after he was sitting there on the table for 20 minutes waiting for the doctor to come in. Okay, and so if you're really well trained, you're going to have a lot of parasympathetic activation. And what this tells us about the difference between our actual resting heart rate and our intrinsic heart rate is that at rest, most of us are in a state right here. And if you want to look at that state right where that black line is, do we have some stimulation from both sides? Yes. We have some sympathetic activation happening and some parasympathetic activation happening. But the important thing to understand is that when we are at rest, our parasympathetic activation is greater than our sympathetic. And therefore, our heart rate is going to be intrinsically regulated a little bit lower than it would be left to its own devices. So let's go back to our statement before of what do we do if we want to increase our heart rate. So if we want to move this way on our figure, what do? Well, the first thing we do is we just remove our parasympathetic. And the second thing we do is we're going to add some sympathetic. So when you're getting ready to run a race and you're standing at the start line, as you feel your heart rate start to go up, that is not necessarily because your sympathetic activation has taken over. It's mostly because that parasympathetic has gone away at first. And then as you start running, that sympathetic is going to kick in and keep that heart rate real high. Okay? What about number 2? How do we decrease? Well, first, we remove our sympathetic. And second, we add in parasympathetic. So now you have finished running the race. Your heart rate is going to start coming down. Well, first, what's going to happen is that sympathetic is going to go away and that heart rate is going to come down. And then over time, after you finish your race, the parasympathetic is going to start to rise again and pull that heart rate even further down. Back to that 80, maybe even a little bit below if you're relaxing. Okay? So that's the intrinsic overall heart rate regulation right there. Let's move on to a little mechanism called the Frank-Starling mechanism. And I'm sure people have heard of this before, but we're going to talk about how basically 4 variables are interrelated. So let's look at our figure right here that we're going to fill in. On the first x-axis at the bottom here, we have ventricular end diastolic volume. Okay? And if we kind of define that, okay, ventricles, we're talking about the ventricle of the heart. We're talking about the end of diastole. End of diastole, if you think about our blood pressure, we have our diastolic and our systolic, right? Our systolic and our diastolic. So that end diastolic volume is going to be at the end of relaxation, all right? Because the diastole is that bottom number. That's when your blood pressure is low. That's when the heart is not beating. So that end diastolic volume is when that heart ventricle is full. Now, on our first y-axis over here, we have stroke volume. So that's going to be the stroke volume that results from having each of these different end diastolic volumes. Now, in concert with that, we also have sarcomere length. So if we're thinking about cardiac muscle, we have sarcomeres within the cardiac muscle as well. That sarcomere length is going to stretch as the volume in the ventricle goes up. So we can use these two x-axes as synonyms for this example right here, because as we get an increase in one, we're going to get an increase in the other one, okay? And it's proportional. Now, the same thing with stroke volume and contractile force. As stroke volume goes up, in order to get that stroke volume to go up, that contractile force has to be greater. All right? So once again, those two things can be synonyms as well. So let's start it off, and we'll start with an end diastolic volume of about 100 mLs. And we'll draw a line of right there. So what this tells us, at point number 1, we have pretty low end diastolic volume and pretty low stroke volume. Okay? Now, if we move up the curve to about 200, we can move up. Very nice. So now we've moved up. We have a higher end diastolic volume. And guess what? Because of that, we also have a higher stroke volume. As you stretch and fill this more, you're going to eject more blood. I'm not, rocking anybody's world right now with these statements. These are pretty obvious, okay? But we're moving in. And now we go to our 300. So we're filling it to that ventricle even more. And guess what happens? Well, you fill it more. and you get a greater stroke volume. You have a greater sarcomere length, and you have more contractile force. Fantastic. So with this, we have a pretty nice linear relationship right there between end diastolic volume and stroke volume. If you stretch this ventricle more and more and more, you're going to, if you think about pulling back on one of those water balloon slingshots, if you want to shoot that water balloon far, well, you're going to pull it back pretty darn far. If you just want to shoot a couple feet, you get pretty close. Well, now I want to shoot it across the street. Well, now I want to be able to hit my neighbor. Okay, that's what you're going to do when you're doing that. The same thing here. If we want more contractile force, we have to stretch that cardiac muscle more and more and more. All right, well then, what happens when we get to 400? Well, this is when everything starts to break down. We have a relationship that looks more like this. Let's change this one. It starts to go down. What happened? We stretched that sarcomere even more, okay? Which previously, by stretching that sarcomere, we got more stroke volume and more contractile force out of it. What happened to cause that stroke volume to go down, even though the sarcomere length got greater and the volume went up? Well, to answer that question, we need to look at the actual sarcomeres, okay? Here we have our cardiac sarcomeres, and we're going to look at these different points, and we can number them right here. 1, 2, 3, and 4. So point number 1, if we look at this, here's our myosin right down the middle, and our little lines on the outside, those red lines, those are the actin filaments. And if we think about this, remember, we have the myosin that's going to be pulling with those power strokes, moving the Z lines closer and closer together. Well, if you think about this figure right here, what's the problem? Well, the Z lines are already pretty darn close. You don't have much room to contract. You can move these very small distances before they're overlapping, okay? So what we would have here is we have crowding of myosin. And we have overlapping of the actin. Let me go back here. Actually, I'll use the eraser. If I zoom in right here, you can see, if you look pretty closely, here's one actin filament. Here's the actin filament from the other side. This right here is overlap. If you have overlap, you're not going to be able to produce force, moving one Z line closer to the other one. This myosin can't get onto this outside actin filament because the inside one is blocking the way. All right, so because of this overlap, we already said we have the crowding of the myosin, actin overlap. These two things result in poor force production. Okay, well, let's move on to number 2. Point number 2, we have a larger end diastolic volume, more sarcomere stretching, greater stroke volume. What has changed in the sarcomere to allow that? Aha! Well, look, now our Z lines are further. Let's draw this one a little bit better. Aha! We have a larger sarcomere now, a more stretched out. Our myosin size hasn't changed. It's just the actin has gotten further apart. Our Z lines have gotten further apart. So here we have less myosin crowding. Less or no overlap. Because if we look at it, do we have any overlap? Nope, it looks like pretty much they just go right down the middle there. And overall, this is going to give us some moderate force. And we'll say that this is kind of during rest. This is what we have at rest, our normal sarcomere length. And why do we look at point number 1? Well, the values that we have here were determined in a lab where they're able to actually take heart muscle, individual sarcomeres, and look at the force production. So that wouldn't necessarily happen in a normal person, but we know that that force-tension relationship actually exists, so we want to put it out there. But at rest, we're at point number 2, where there's minimal overlap and some moderate force production. Right now, our hearts are beating, getting oxygen and blood to the rest of our body, and that's a good thing. But we have times where we need more. So if you look at point number 3, this is during exercise. Our end diastolic volume is greater. We're getting more blood returned back to the heart, and therefore we're stretching those ventricles even more. Look at all this space right here. So in number 3, we have no crowding. And no overlap. And this is going to be high force production during exercise. And last but not least, we have point number 4, where our force production has actually gone down despite the fact that our sarcomere length is even bigger. If we look at number 4 in comparison to number 1, it's probably twice as long. So if you think of our analogy with the water balloon slingshot, if you pull back even further, shouldn't you be able to shoot that water balloon even farther? Well, this is where the analogy breaks down. Okay, basically what's happening is you've now pulled that too far, and the slingshot is going to snap, and that water balloon is going to just kind of slap back and hit you in the face. All right, and that's exactly what's happening here. For point number 4, we have too much stretch. And what we have because of that is no room for the myosin to bind. Let's zoom in here and look at our myosin cross bridges, specifically between points number 3 and number 4. If we go here, and I'll make this in blue, here's our myosin. Let's do it a little bit brighter blue. Let's make it a little bit bigger. Here's our myosin right here. The cool thing you can see is look at all these cross bridges. Well, what's immediately adjacent to each of those cross bridges? Well, actin. If we want to move the actin Z lines closer to one another, our myosin better be able to interact with that actin. Well, what happens when we move down here and we have even more stretch? Look at the first 4 cross bridges going in either direction. They don't have any ability to interact with the actin. These guys on the end maybe just might be barely hanging on, and they can produce a little bit of force going in that direction. But these ones are useless. So too much stretch means that our actin and myosin cannot interact the same way they normally would. So number 4, too much stretch, no room for myosin to bind, and overall, we can say that this occurs, during our supramaximal exercise. And this is one theory why exercise has a max, is because basically we've reached the point at we cannot improve our cardiac output anymore. We are returning more and more blood, but we're not getting more and more blood out because we've overstretched our ventricle. Our ejection fraction has gone way down. We're not increasing the amount of oxygen we're supplying to our muscles. We're not increasing the amount of oxygen molecules at the end of the electron transport chain. Therefore, we can't create any more ATP. Overall, this results in no benefit, and this is not very common during exercise, but this could happen as well. So we don't want to stretch these too much. The Frank-Starling mechanism, what this is telling us is that as we increase our end diastolic volume up to a point, we get more ejection. We get more blood ejected. And that's a good thing if we're moving from rest to exercise. However, we also have to know with this that you can get too much of a good thing. Too much stress is going to result in a lower stroke volume and less contractile force overall. Okay, we'll pick it up on Monday. Nice little quick one here. 2 more lectures left. Keep sending me in those questions about the exam, and I'll see you on Monday.